Hello everybody, we're going to look at a new unit today on radioactivity. We're going to be doing this for the next 2 or 3 weeks. I find it really interesting. As ever, what I'll get you to do is complete the tasks. I'll ask you to press pause on the video. There'll be a pop-up, complete the task and press play when you're ready to carry on. So, before we start and going into the complexities of radioactivity, we need to have a look at the model of the nucleus. So before the nucleus of the atom was discovered in 1914, scientists believed the atom was like a plum pudding. Now, scientists believed that negatively charged particles suspended in a positively medium, and we had not positively charged medium, and they had not discovered that protons and neutrons existed. They only knew about the electrons. Now, the reason why we likened it to a plum pudding is if you can imagine the sponge being the positively charged medium, and the plums inside the pudding representing the electrons which are suspended in this positively charged medium. Don't forget, electrons are negatively charged. Now, we had a scientist called Ernest Rutherford, and he conducted some experiments with an alpha radiation emitter and some gold and some detectors. Now, what actually happened is a lot different to what he expected to happen. So we're going to have a quick look at this now. Using an interactive animation. So here we've got our plum pudding model with our positively charged cloud, if you would, or our positively charged sponge. And we've got our electrons being represented by the little blue dots inside the positively charged sponge. So we'll turn our alpha emitter on. Now, the alpha particles, this is what expected to happen. He expected the alpha particles to travel straight through the plum pudding model of the atom. They expected nothing to happen at all. However, what actually happened is the following. So if we take it on a nucleus scale, so this is looking at the nucleus, turn our alpha particles on. What actually happened is, as the alpha particles got closer to the nucleus, they deflected away. Now, what I can tell you is that the alpha particles are positively charged, and the nucleus, which contains protons and neutrons, is positively charged. Remember, a proton is a positive charge, a neutron has no charge. So overall, the nucleus will be positively charged. Now, if we look at that on a different level, so on this in simulation, each one of these little dots in the middle represents the nucleus of an atom. Each one of the purple tracers represents an alpha particle. Remember, alpha particle is positively charged and the nucleus is positively charged. Now, what happens when two alike charges interact? They repel. And this is what's causing these electrons to rebound and deflect quite aggressively. If we concentrate on this one here, the closer it gets to the neutron, the more it deflects. Now, you'll also notice some of the alpha particles are passing straight through the atom with no deflection whatsoever. Now, from this, Ernest Rutherford was able to ascertain that the majority of the atom is made up of space. There is nothing there. So we've got our nucleus here. We've got nothing at all until we get to our electron shells, which are here. Remember, electrons are negatively charged. So again, if we watch, the closer it gets to the nucleus of the atom, which is positively charged, the more it deflects. The further away from the nucleus, the less force there is, and it passes straight through. This would suggest that the center of the majority of the atom is made up of nothing at all. Okay, so we'll go back to our slideshow and we'll summarize that verbally. So bear with me 1 second. So, you find the alpha particles at a sheet of metal and record where they deflected on the detecting screen. So this is a mock-up of this experiment. You may well see this in your exam papers. So here's our alpha particle emitter. It gets fired at the gold foil. He expected everything to pass straight through. However, it deflected quite substantially all over the place. So he expected all these alpha particles to travel through the metal, but he noticed that the alpha particles deflected off the metal in different directions, some even bouncing back directly to the alpha radiation emitter. So what did it actually show Rutherford? Well, this is what your task's going to be. So what I'd like you to do is complete task 1. I'd like you to draw and label the model of the atom then use this to help answer the questions on Rutherford's experiment. Remember, in the atom, you will have protons, neutrons, and electrons. So answer these questions first, and then you can write your conclusion. So what is the charge of an alpha particle? What is the central part of the atom called, and what are the names of the two particles which make this up? What is the overall charge of the center part of the atom? What is the atom mostly made up of? And what happens when alike charges come together? So once you've answered those questions, use those answers to form a conclusion to the experiment that Rutherford did. So press pause on your video and complete task 1 in your worksheet for me. Press play when you're ready to continue. This next section, we're going to look at what we know as peer review. So Rutherford's nuclear model of the atom was very quickly accepted because of the following reasons. It agreed exactly with the measurements Geiger and Marsden made in their experiments. Now, Geiger and Marsden, I believe they were Rutherford's assistants. Rutherford got those guys to repeat the experiment over and over and over again. What they noticed is that the results agreed with Rutherford's. It explains radioactivity in terms of changes that happen to an unstable nucleus when it emits radiation. And it also predicted the existence of the neutron, which was later discovered. Now, a little sort of thought experiment to yourself. What difference would it have made if Geiger and Marsden's measurements had not fitted Rutherford's nuclear model? Well, it wouldn't have been accepted, would it? Part of science is peer review. If you come up with a new sort of discovery in science, other scientists have to be able to verify what you have done. Then it becomes accepted. The ultimate insult in science is not somebody saying your work is wrong. The ultimate insult in science is people ignoring your work in the first place. So, your next task. Some scientists are unconvinced and still want to hold on to the plum pudding model. Explain why these scientists are incorrect. You must include in your answer the structure of the atom, how this structure was confirmed by Rutherford, and the evidence that supports this theory. So we've got a little diagram there. If you want to go back to the previous slides for help, feel free to do so. So press pause on your video and complete task 2 on peer review. Press play when you're ready to continue. Now, this topic, structure of the atom, is guaranteed to come up on either your chemistry papers or your physics papers. It's one of those things that goes into both. So you really need to have a good understanding of the structure of the atom. So in this question, you will be assessed on using good English, organised information clearly, and using specialist terms where appropriate. Describe the model now used for the structure of an atom. In your answer, you should give details of the individual particles that make up an atom. There are 3. Include the relative masses and relative charges of these particles. So remember, there's going to be a different mass for each of the 3 particles and different charges for each of the 3 particles. Do not include a drawing in your answer. If it asks you to not include a diagram, please don't do it. Make sure it's written in text. Now, if you want to do a little bit of research on this, that is absolutely fine. So let's say that this is a 6-mark question, so I'm looking for 6 pieces of information. Press pause on your video and complete task 3 and answer the exam question. Press play when you're ready to continue. So now we're going to go into radioactivity. Nuclear radiation is caused by changes in the nucleus. Decay is a loss of protons, neutrons, or electrons from the nucleus to become stable. So here we've got 2 examples of 2 well-known atoms. We've got a carbon atom, which is made up of 6 protons and 6 neutrons in the nucleus and 6 electrons in the shells. And we've also got oxygen. We've got 8 protons, 8 neutrons, and 8 electrons. Now, if an atom has a different amount of protons than it's got neutrons, it wants to become balanced. Now, the scientific version of this is radioactive decay is a set of various processes which unstable atomic nuclei emit subatomic particles. Decay is said to occur at the parent nucleus and produces a daughter nucleus. It is a random process. In other words, it's impossible to predict the decay of individual atoms. Now, if we take a carbon-14 atom, in the nucleus of a carbon-14 atom, we have 6 protons, but we have 8 neutrons. Now, what the atom will do is go through radioactive decay to make it balanced, to make it have 6 protons and 6 neutrons. Radioactive materials, most atoms are stable. However, radioactive atoms are not. They are unbalanced and unstable. It's normally because we've got a different amount of neutrons to the amount of protons. For example, we could have 8 protons and 10 neutrons. That would be an unbalanced atom. If it was 8 protons and 8 neutrons, well then it would be balanced. There would be no radioactive decay. They want to become stable. So to try and achieve this state, they emit energy in the form of radiation. Now we've got 3 types of energy that gets emitted, 3 types of what we call decay. So I'm going to go through all 3. So an unstable nucleus can decay by emitting an alpha particle, a beta particle, and a gamma ray, or in some cases a single neutron. So alpha particles, if the nucleus has too few neutrons, it will emit a package of 2 protons and 2 neutrons called an alpha particle, often represented in a diagram like this: 2 neutrons, 2 protons. An alpha particle is also a helium-4 nucleus, so it can be written as the following ways. It can be written like this: 2 protons, and our atomic mass number is 2 protons plus 2 neutrons, giving us 4, and then we write He because that's a symbol for helium. Or we can write it this way. Again, the numbers are the same: 2 protons, and then we've got 2 protons plus 2 neutrons, giving us 4. So 2 protons being the atomic number, 4 being the atomic mass number. But instead of writing He, we write the symbol alpha. Alpha decay causes the mass number of the nucleus to decrease by 4, and the atomic number of the nucleus to decrease by 2. So if we take a uranium atom here, we have an alpha particle which is emitted, 4 and a 2. Now we can see here the mass number is 238 and the atomic number is 92. Remember, the mass number is the amount of protons and neutrons added together. The atomic number is the amount of protons only. 4 and a 2 gets emitted as an alpha particle. What we are left with is 234 for our mass number and 90 for our atomic number. Take 4 away to get that, take 2 away to get that. Next, we've got our beta particle. The nucleus has too many neutrons. A neutron will turn into a proton and emit a fast-moving electron. This electron is called a beta particle. This process is known as beta radiation or beta decay. A beta particle has a relative mass of 0, so its mass number is 0. And as a beta particle is an electron, it can be written as either this symbol here with a 0 and a -1. Do not worry about the -1. We're going to come to that in the future. I just want you to know that this represents a beta particle. Or we can represent it this way with a 0 and a -1. But in this case, instead of an E for electron, we give it the symbol beta. The beta particle is an electron, but it has come from the nucleus. It has not come from outside of the atom. Electrons are not normally expected to be found in a nucleus, but neutrons can split into a positive proton, same mass but positive charged, and an electron, which has a negative charge to balance the positive charge. It's then ejected at high speed, carries away a lot of energy. Beta decay causes the atomic number of the nucleus to increase by 1, and the mass number remains the same. We will go into the maths of it in a different lesson. All I want you to concentrate on for now is that this represents beta decay. And then we've got gamma decay. After emitting an alpha or beta particle, the nucleus will often still be too hot and will lose energy in a similar way to how hot gas cools down. Hot gas cools down by emitting infrared radiation, which is an electromagnetic wave. High energy particles will emit energy as they drop to lower energy levels. Since energy levels in the nucleus are much higher than those in the gas, the nucleus will cool down by emitting more energetic electromagnetic wave called a gamma ray. Gamma ray emission causes no change in the number of particles in the nucleus, meaning both the atomic number and the mass number remain the same. Any atom that goes through any kind of decay will also emit gamma decay. It does nothing to the atom, it's just getting rid of the excess energy. It can be written as one of the following ways. We can write it as a strange Y, this is the symbol for gamma, or we can put some numbers to it, but they will be 0 and 0 because it changes nothing in the nucleus of the atom. And again, this is the symbol for gamma. If we looked at a uranium atom again, we've got alpha decay, gamma decay, and we've got our key there. So, the amount of radiation an atom loses can be measured using a Geiger Muller counter. Use the video link on your worksheet to view a demonstration of how this can be achieved. So, if you go into your worksheet, just under where I've written task 4, there'll be these links. Have a look at the videos and it will explain it really well to you how to use a Geiger Muller counter and what background radiation is. So, properties of nuclear radiations. This is what we're going to concentrate on today, not the maths part, purely this. So, the different types of radiation are often compared in terms of their penetrating power and their ionizing power, and how far they can travel in the air. All types of radioactive decay can be detected by a Geiger Muller tube or a GM tube. The radiations ionize the gas inside, and resulting charged particles move across the chamber and get counted as charges, rather like an ammeter. So it's just a way of measuring things. You've probably all seen the videos now, and you've probably seen it in films where you hear it click. The faster the clicks, the more radioactive the symbol is. Now, this is the really important part of today. Alpha, decay, we've got our symbol. It's penetrating power. It stops at skin and paper. However, it's got really high ionizing power. It can really cause some damage. An alpha decay emitter will only go less than 5 centimeters in the air. So if we look at our diagram, we've got our alpha emitter here. It will not go past the hand. It won't get through it. Now we've got beta decay. So we've got our beta. There's our symbol. It's penetrating power. It will stop at 3 millimeters of aluminium foil. It's not got particularly a high ionizing power, so it's not particularly dangerous in terms of comparing it to alpha. And its range in air is approximately 1 meter. So if we go back to our diagram, we've got our beta decay. It goes through the hand, but it gets stopped at the aluminium sheeting. And then we've got our gamma decay. Its penetrating power, it will stop at lead and concrete. It's very low ionizing power, and it has got a range in air of 1 kilometer. So again, if we go back to our mock-up, we've got gamma, goes through your hand, through the aluminium, stops at lead. Okay. However, in terms of the 3, it doesn't cause much damage. So the nucleus loses electrons, protons, or electrons to become stable. Alpha radiation, 2 protons and 2 neutrons. Beta radiation loses 1 electron. Gamma radiation is just energy. When this happens, energy is released, and it's completely random. We have got lots of background energy at radioactivity. It can be measured everywhere. Down in Devon, it's a little bit higher than what it is normally. However, there's probably more radiation in a banana than what you're subjected to every day, so it's nothing big to worry about. Again, we've got our picture. Alpha gets stopped at paper. Beta will go through paper and get stopped at aluminium or tin foil. And gamma will go through pretty much everything, but it will stop at lead. So I'd like you to complete task 4 on the different types of radioactive decay. All I want to know is what their penetrating power is, what their ionizing power is. Once you've done that, press play on the video to move on to where we actually use these types of decay in the industry. So, how can radiation detect a fire? Now this is where we actually use it. So it's got a long-winded way of getting there, but this is the real-life applications of radioactive decay. Smoke alarms contain a weak source of alpha radiation. The alpha particles ionize the air. This allows current to flow. If there is smoke present, it interacts with the ions produced by the alpha particles, and ionization is reduced. This means that less current is flowing through the air, which causes the alarm to sound. That is it. So our beta particles, they allow the current to flow, smoke gets in the way, it stops the current, which starts an alarm. Now we've got beta decay. This can be used in paper mills to judge the thickness of paper. Now, or it can be used to judge the thickness of aluminium foil. So if we look at the foil, we've got beta emitter and then we've got a detector. If the foil gets too thick, the detector can't detect the beta decay. So the rollers will adjust to make the aluminium foil thinner. If it detects too much beta decay, well then the rollers will open up a little bit to make the aluminium thicker. And it's the same kind of process on the paper. You can control the thickness of the paper by using a radioactive source and a detector. The amount of radiation will dictate how wide or close together these rollers are, which controls the thickness of the paper. And we've got this one here. So if a little radioactive material is put into a moving liquid, the path of this liquid can be tracked. It can be used in testing blood flow, tracking underground streams, and following the movement of silt in rivers. The gamma source is placed in a metal casting and a Geiger counter moved over its surface. If there are any cracks in the metal, gamma radiation can get through and can be detected. And again, we've got another explanation there of our smoke alarms. So all 3 can be used in industry really effectively. So your final task is to choose one of these, or you can choose this one. How can you find a leak in an underground pipe without having to dig up the whole pipe? We have water pipes absolutely everywhere, all over the country, because this is what supplies the water to your house. If you've got a leak in one, you don't know where, how can you find it? What would you do? So imagine you're working for Severn Trent Water. There is a burst water pipe in an area of 30 metres long. The pipe is buried 2.5 metres deep. Use your knowledge of radioactive decay to speed up locating where the break in the pipe is. Explain what you are doing to Jon Snow, because he knows nothing. You have got a choice in which one you do. You can talk about the smoke alarm, you can talk about the paper. I'd really like you to have a go at this, because this is something new, it's something you can use, and it's something that does get done. Okay? And that's the end of it. Thank you very much. Any help that you need, please get in touch.